So, in this video we're going to talk about the reactions in phenol. Let's start with the easier ones. So, just like benzene, just like alcohol, phenol reacts with sodium metal to form sodium ethoxide. What? No. It forms sodium phenoxide and hydrogen gas. It's common, it's simple, nothing major in this reaction. Well, yes, it is in Toller state. But there's a different one, which is that phenol can actually react with sodium hydroxide to form the same thing. Sodium phenoxide and water. Why is that significant? Relatively, it's because if you try to react benzene with sodium hydroxide, it doesn't work. So this is one of the points that could show why phenol is more reactive than benzene. Right, so we could then we could then build up on the sodium phenoxide ion. If we add hydrochloric acid concentrated, we could actually turn it back into phenol. Well, is that of any importance? Yes, when we're doing organic synthesis, but there's another point that I would like to add on that sodium phenoxide. Remember how in the last video we talked about the acidity of carboxylic acid and phenol? We could actually prove that in an experiment. It's pretty easy. Let's name it the liberation of carbon dioxide. So what you do is you've got some phenoxide ion, you've got some water, you've got a delivery tube, and you place some carbon dioxide in. What happens is the phenoxide ion actually turns back to phenol. Well, the equation, it's something like that. So we've got carbon dioxide plus water, that gives a phenol and sodium hydrogen carbonate, or whatever you want. The point here is, it shows that the carbonic acid here, because as we all know that carbon dioxide associates with water to form carbonic acid, the carbonic acid could actually displace the sodium ion in the salt to form back to phenol here. So that means, and that signifies that if we want to react phenol with sodium carbonate, the reaction doesn't work because phenol is not strong enough to displace sodium carbonate. It's really like remember how you learn in halogen when, let's say, chlorine reacts with potassium iodide and they form potassium chloride and iodine. I'm not going to balance equations, it takes time. But let's say that now we have iodine, we react it with potassium chloride. It doesn't give a reaction because iodine is not strong enough to displace chloride really. So this is the same case here. Phenol is not strong enough to displace sodium carbonate, but meanwhile carbonic acid in the other form, it could displace the phenoxide ion back to phenol. But why am I talking about that? Because from GCSE we all know that carboxylic acid could react with carbonate ions, or with sodium carbonate or sodium hydrogen carbonate to form something like, if I give you an example, let's say that I've got ethanoic acid and I add sodium carbonate, and that gives sodium ethanoate, yeah? Sodium ethanoate and carbonic dioxide and water. So that means ethanoic acid can displace sodium hydrogen carbonate or sodium carbonate, and whereas the carbon dioxide and the water is not able to displace back sodium ethanoate. So the point I'm trying to make here is it shows ethanoic acid is more reactive than phenol, and which it links back to the acidity of how the OH bond electron density in ethanoic acid is higher when we compare it with phenol, which is lower. Now, let's move on to another example, which I find more interesting, which is the esterification. Well, in normal cases, we know that, we could use acid chloride and we react it with an alcohol to form ester. We could also use carboxylic acid and we could use alcohol to form an ester. Well, if you think about phenol, it has a hydroxy group. It could also be an alcohol and it could also react. Well, but if we try to use phenol and we react it with, let's say, ethanoic acid, you see no reaction. So why is that? There's really two main reasons that, and it all regards with phenol and the carboxylic acid. So if we talk about phenol first, we've mentioned before how in phenol they overlap. So I'm not going to draw brilliantly, but you know, it's like a tennis racket. There is a extended pi bonding electron system in phenol. So the lone pair of electron in the oxygen atom, it delocalized in the ring as well. So in esterification, as you might know that it is a nucleophilic substitution, nucleophilic condensation reaction. If we use this lone pair of electron and we delocalize inside, it is actually it reduces the ability for oxygen, or for this species really, to act as a nucleophile and use it as for a nucleophilic attack. So I know it's a bit wobbly just now of what I've said, so I'll say it again. So the lone pair of electron in the oxygen, it delocalized in the pi bonding electron ring. So that means the oxygen atom is less likely to be a nucleophile, or really the whole species of phenol is less likely to be a nucleophile, because if you think about it, it spends majority of the time spending here, but whereas we really need it in the oxygen atom. So that is the first reason. The second reason is in carboxylic acid, and it's something weird again. I looked it up myself yesterday and I still don't really get it, but I'll try and explain it. You know how we talked about this weird lateral p orbital overlap? This actually causes, or not causes, but carboxylic acid also has something called a conjugation of lone pair, which you could say it's caused by this, and it's caused by something called resonance. Well, we all know what resonance is, but what is a resonance in carboxylic acid? Well, let's go R here. So what happens is the pair of electron in the C double bond O bond, it moves to this oxygen. No, it doesn't move here. Yes, it does. The main reason is because I forgot to add the lone pairs here. So I'll say again, the C double bond O pair of electrons move to the oxygen, and one of the lone pair of oxygen move into this C single bond O. So this causes a resonance of something like that. How in this oxygen, you have now got six electrons, so 3 pair of lone pair, and in this oxygen, you've only got a pair of lone pair of electrons. So it creates a negative charge here and a positive charge here. Well, it's still neutral, but it causes this resonance effect. So the importance of this is really that it reduces the electropositivity of the carbon atom. Why is that? As we know that there's dipole moment here, but this resonance thing and this weird lateral p orbital overlap causes the negative charge to be more spread out, yeah? And the carbon atom is not that electropositive anymore, so it's less susceptible for the electrophilic attack. Well, so how can we actually allow them to react? Well, we can't, but we could do modifications. The first modification is if we could turn phenol into something more negative. So if we add sodium hydroxide, it gives the salt, yeah? Plus water. But this is a good configuration of initiating a reaction, because the negative charge here is now more concentrated, as you can say it, relative to the phenol here, where it's not that concentrated. So the negative charge is greater here, so it could act as a better nucleophile. And for carboxylic acid, which is our second point, if we add SOCl2, I don't really know the whole name for this molecule, but if we add this weird compound, we could turn it into an acid chloride. And as we know, acid chloride is really, really reactive. So it's of no doubt that these two might react to form an ester. So let's assume that they actually reacted. What are they going to form? They're going to form something that I'm going to use a green pen to draw it, which is something like that. It's still an ester, but this ester is known as phenyl ethanoate. Phenyl ethanoate. Right. So, just a few more reactions for phenol, and that will really do. So, phenol can undergo esterification, and it could also undergo electrophilic substitution. If you think about it, there's still a benzene ring in phenol, and the whole process of how benzene undergoes electrophilic substitution is literally the same here. So let's say that now we've got nitric acid. It undergoes electrophilic substitution, and this forms something like that, and it forms something like that. Oh god, it's too ugly, sorry. And it forms something like that. Now, there's quite a lot going on here, so I'll try to explain in a bit more detail. The OH group in phenol, it actually has a directing effect for other substituents at the places 2, 4, 6. So what does that mean? It means that if we call this 1, 2, 3, 4, 5, 6, these are the 3 main places where the substituents are going to go if phenol needs to react under electrophilic substitution. Well, this is the first significance of the reactions in phenol. And the second thing is, we talked about nitric acid. Benzene could also react with nitric acid, right? But remember the condition in benzene. It's concentrated sulfuric acid, concentrated nitric acid, and something else. But the point is, we need to use dilute nitric acid here, comparing to the concentrated here. This also proves the point that phenol is more reactive than benzene because of all the extended pi bonding electron system, cloud, whatever. It is really all down to this point that makes phenol so not so special, but you get what I mean. Yep. So that is the reaction with nitric acid. Now, if we move on to reaction with bromine, exactly the same thing. But this time, I'll like to add it in excess. It doesn't really need to be excess, but the reason I want to show why it's in excess is because this weird thing here is actually a white precipitate. We also need 3 hydrogen bromides. So the purpose of this white precipitate, which is defined by nature, is really useful because if we want to know whether a compound XZY, did I just write XYZ? Anyway, if a compound XYZ needs to be sort of like, it needs to be confirmed whether it's a phenol or something else, if you add bromine directly and it forms a white precipitate, it must be phenol. Or it can be phenol, it can be something else as well. But yeah, that's a really good tool for you to identify. So that is really what I want to say. And to finish off, I would like you to know how to test for phenol, which I've said it, a few seconds ago. To use bromine, if there's positive result, it would be a white precipitate. We could also add iron chloride. This gives a purple solution. Well, if you want to know what this purple solution is, it's really a complex between iron chloride and phenol. That is really all you need to know about phenol. There are some slightly minor details I haven't gone through, but the major points are here, and as you can see, phenol is not that hard. Ultimately, it's all about remembering conditions and remembering the specialities of phenol, and that's really it. So yeah, thank you for listening.